So today we'll actually go a little bit over the important material for the midterm. Largely will comprise the material today based on the questions that you asked on Piazza and during the office hour. So who better could help you go through those questions than the people you asked those questions during office hours. So today we'll actually have 3 of our TAs give different repeat sessions based on the questions they've gotten from all of you during office hours. So if you have any questions today, during the material, we don't really have to go through all of it. The main point is for you to clear up all the remaining confusions and really understand the major techniques for implementing BackProp. So today it should be really an interactive session. If you have questions that halfway through the class you still feel like aren't being answered, you can also just interrupt us any given moment in time, and we'll try to go over your questions, rederive stuff on the board, and help you get through the material. In the midterm, we'll actually have to split up the class because we want to ideally have one space between all the students. When you take the midterm, it's going to be a closed book midterm, so you actually have to just really understand the material, maybe memorize some things if you don't think you can derive them from scratch again. And we'll announce to you on Piazza and probably over the mailing list how we split the students, probably based on last name of letters and some such system. Are there any questions about today's class, past classes, and organizational things? No? All right, so one of the lecture halls will be this one here, and then we'll probably have to send some students to another class. So do check Piazza on the mailing list on Tuesday evening to know where to go for Wednesday's class.
Yes. My question is how, up to what lecture does the midterm material?
Sort of up until last week. But there are 2 lectures where I explicitly said, you don't necessarily need to know all the, core details and full derivations of everything. But even until, last week, you should have some idea of, what's going on, what's the difference between a recursive and a recurrent neural network, what's a gate, and all those kinds of things. Like, you should still have some idea of what these things are useful for. But maybe, we're not gonna, also you can just do the math, right? Like, how long does it take you to derive, like, a full LSTM and every single, index of every single gradient of a full LSTM, right? And it would take a little too long to be able to ask a bunch of different kinds of questions. But with that, I'll let Rohit take over the first part of the class. Oh, one more question.
Okay.
There's unfortunately no practice midterm, no. The practice midterm is really all the times in the class when I said, and this will be useful to look at. Those are things to look at. And today's session. So if you have any kinds of questions, today's the day. Yep.
Is it like for the format, or is it just going to be like short answers?
There will be derivations. It won't be just like multiple choice, kind of yes, no kinds of questions. There'll be some of those, but you'll actually have to derive some stuff. All right.
Thanks. Hi guys. So I'll be reviewing the basics of neural networks, including the terminology, what a forward pass is, what backpropagation is, and most importantly, how to do all this really, really quickly. Like Richard said, the exam is going to have maybe potentially derivations, other problem solving. So you really want to be comfortable with these topics, and you don't want to be doing derivations and figuring out how backprop works for the first time in the exam. So I'll try getting to that point rather quickly where you can do these little tricks and see how the error flows backward. But we'll start with the bare basics right now. So I'm going to talk about what a neural network is, use an example, talk to you about the terminology, and then we'll do 2 examples. In the first one, I'm just going to use the chain rule first in order to do basically calculate the derivative of one of the parameter updates. And then I'm going to talk about how to move to the modular error flow, which is something we noticed in the office hours that not everybody is completely comfortable with. There's a lot of confusion about what delta is, where exactly we calculate it, where exactly we measure it. So we're going to talk about that, and then I'm going to do a second example where we use just the plain concept of delta. and apply chain rule, well, based off of that. All right. So neural networks are like one of many different types of nonlinear classifiers that are there, and by that I only mean that the decision boundaries that are formed are nonlinear. So they're actually really powerful. And the most common design of neural networks just involves stacking affine transformations followed by pointwise nonlinearities, and you just repeat that over and over again. And then at the end, you just make a final prediction. So that's just a neural network, and you should already know this. This is what a fully connected neural network would look like. As I speak, I'll call something like this a 4-layer neural network. You could also call this a 2 hidden layer neural network. You could call this a 2 10 10 3 neural network, which then completely characterizes the fully connected nature of the network. Anyway, so this is the first example I'm going to be working with. It's a really simple one. It's from the notes, so if you've read it, you should be familiar with everything we've done in it. This is simply a 3-layer network. There's one hidden layer with 2 units over here. So the terminology I'm going to follow is going to be something like this. There's model inputs all the way to the left. Those I'm going to refer to as X. This is a single data point. This is not multiple data points, but everything that we speak of can be actually easily extrapolated to multiple data points. But this is a single data point with 4 values. So 4 index points. You can retrieve each of these. These are each scalars. There's a model output to the right over here. This is the S. This is a score. These are the activation units. Notice that I've called even the stuff on the left and on the right, all of these activation units. They're not really doing anything right now much. They're simply forwarding the value that they receive. So I've put 1 on top of these, while the ones inside are nonlinear units. Now, it might seem like I'm trying to confuse you with this part, but really all it is doing is just maintaining the notations for the sake of consistency, so that the equations we reach at the end of this part, you can apply them almost blindly to any of this. All right, so activation unit. We have an activation unit which we typically draw on the graph something like this. You have multiple inputs, you draw a sigmoid, and then you draw an activation coming out of it. But really what's going on is you take multiple inputs, you sum them up, that produces a Z, and that you pass through a sigmoid, and that produces an activation. So just keep this in mind every time you're working with an activation unit, that it's actually a 2-step process that's going on. And you can write the value of Z simply as a linear combination of the activations of the previous layer. The parenthetical superscript that you see over here is just indicating the layer that we're working with. So you can see that the activation of layer 2 is a result of the input, the linear combination at layer 2. This is just the subscript. On the other hand, is just notation for the neuron number, the neuron count that we're working with on a particular layer. So that's why A subscript 1 superscript 2 is basically just the activation, the first activation unit of layer 2. All right, so let's talk about forward pass first. Here we see, I'm going to do it in a stepwise manner. We start with the inputs x1 through x4. This is a single vector again. Nothing really happens from this point to this point because the summation that we spoke of in this slide is just receiving a single input. So z1 does in fact equal x1 in this case. All right, and then we pass it across this first activation unit, which again is not really doing anything at this point, since again the activation is literally 1, so it's just multiplying the input by 1 and forwarding it through. Then comes the interesting part, which is where you basically propagate it through this affine transformation. So all you do is you take the inputs and you multiply it with these parameters W. There are 8 parameters in this case, and that generates the the linear combinations Z1 2, Z2 2 right here. And you'll see that this can actually be represented as just simply a matrix multiplication, and you should be familiar with this part too so far. So we'll just say that Z2 is basically a product of the matrix W1, which is mapping activations of layer 1 to Z2. So far so good. All right, so we're just going to call this an affine transformation and move on. So at this point we have Z2, and what we do is we apply a pointwise nonlinearity sigma to each of these. So at this point we're not really doing any affine transformations. Instead we're taking each element of the vector Z superscript 2 and just applying a sigmoid transformation to it, and we're retrieving these activations of the second layer, A2. All right, and then we do the exact same thing. We map it outwards and we get Z3, which is a product W2A2. And at the end, again, we have nothing really happening here. We just basically forward it through since we're using a max margin loss in this case. So it's basically just getting multiplied by 1, and your activation is simply your linear combination Z. All right, so that's how forward pass works. So now I want to talk about doing a back propagation, and I particularly want to work on this parameter weight here, W14. So I've drawn it in red right here. So I basically want to see if there's an error propagating backwards, an error S propagating backwards, what would be the gradient with respect to this particular weight, the weight that connects A4 superscript 1 to Z1 superscript 2. So let's try doing this the chain rule, using chain rule, and this is the harder way of doing things, but we'll eventually reach a much simpler way of doing it. So this is typically what you're used to. You're used to opening it up, write ds with respect to, do the partial of ds with respect to dz13, which is right here, then do dz1 with respect to da12 right here, and then the error with respect to z1, so that's the third term here, and then the fourth term, which is dz1 with respect to the weight itself. So this is pretty much as you can break this down. So this is simply 1. This first value is simply 1 because really there's no transformation really happening from here to here. This is a single unit 1. This could be different if you're working with softmax losses, so you've encountered y hat minus y in that case. So in this case it's just simply 1. Then you have the second term, dz13, with respect to a12, which is basically the transformation from here to here. So if we open this linear combination Z and write it in terms of the matrix multiplication that it's a result of, you basically get this. This should be 2 right here. Sorry about that typo. I'm going to fix that. And you'll see that there's only a single unit over here, A2, which is this single unit here, which is dependent on the partial that we're trying to take it with respect to. And so you're basically left with W11 superscript 2, and then you're left with 2 remaining elements that we still need to figure out. dA1 with respect to dz1. So this was basically a sigmoid in the forward pass, so now we'll have a sigmoid derivative in the backward pass. So that's this. Now this is just sigmoid times 1 minus sigmoid. I'm not going to open it up just for the sake of real estate on the slide. And that leaves us with this last element, dz1, so the linear combination with respect to the weight matrix element. And again, we can open this entire thing up right here, z1, with respect to the 4 inputs that it receives. And you'll see that, again, there's only a single dependency on W14, and that's this one, so you'll be left with. All right, so any questions so far? Does all this make sense? Yeah? All right, thanks, Richard. All right, so now this is where things get really interesting, and we'll start talking about the modular error flow. This is what we call delta. Basically, it's the error propagating backwards times the local gradient at this point. So every time I reach a point right before a neuron, I start calling it a delta. So same with, there's a delta over here, there's a delta over here, there's a delta here. These intermediate values are not really called deltas, just for the sake of notation, at least in my slides. So anyway, I call this delta sub 1 superscript 2 because it's this is the error at z sub 1 superscript 2. This is a combination of the local gradient at that point times the matrix multiplication, the error that it's receiving from the forward. And you can see that the gradient that you receive over here is basically just a product of the input that weight forwarded as well as the gradient that it received in the backward pass. So yeah, this is exactly what I just told you. So in order to calculate this value, we basically needed the signal that was forwarded by W14 superscript 1, the error that was propagating backwards, which is W11 superscript 2, and the local gradient over here. And you take a product of these 3 elements and you should be able to get the derivative. Now this is rather cumbersome, and if you had to do this for every single element of the matrix, I mean, you could do it just in the same manner and you'll end up with this formulation right here, this matrix over here. And it's kind of cool how this can be written as an outer product just as a result of linear algebra. So you'll see that it can basically be written as a delta vector, a column vector. So this element right here is the error sitting right here, and this lower element right here is the error sitting right here. and you just want to do an outer product with the inputs that were forwarded by this matrix W. And that's how you can get the gradient update with respect to all of W. And this is nothing but doing exactly the same thing for all 8 elements. Does that make sense so far? All right. So now I want to just get into delta, because that's what you should really be working with in your midterm, because it'll make things much easier, much less prone to errors, and much cleaner. And in fact, if you see any modern implementations of forward passes or backward passes, even in the numerical methods of the topics we're talking about in class, they always use the matrix methods as opposed to doing it at an element-wise, just for efficiency. So delta is, like I said, when you do a forward pass, which I'm going to refer to, things in green are typically forward pass, backward is in orange. So when you do a forward pass and you get a Z12 and then you pass it through a sigmoid activation unit and you receive something like this, A12, for that exact same location Z, the backward error is called delta 12. So I think I've already mentioned this one. So this is exactly what it is. So if you were ever wondering what delta is, it's the error exactly at this point. So if you were to do backpropagation using error vectors, you'd basically need 2 different patterns. And the first thing is, if you're receiving an error into a pointwise nonlinearity, or even a linearity for that standpoint, anything that's doing a pointwise application on your signal, or signal in the forward pass, or the error in the backward pass, if the error coming backwards was x, you'd basically get the sigmoid derivative times x going backwards. This is just a rule, and we actually did this in the chain rule method as well. It basically is just a result of the partial with respect to the sigmoid. And the second thing you might notice is that if you have an error delta coming into a unit which then redistributes, so typically what we were doing was we were summing over these values and calculating a z in the forward pass, which is why the z over here is basically a sum of these 3 elements. What you would have is that this delta would propagate backwards with exactly the same weights, W1, W2, W3. Now note that these are not derivatives with respect to W1, W2, W3, but they will be used for downstream derivatives. And if you were to do the derivatives with respect to this, you would do the outer product method we just spoke of. If you wanted to calculate the derivative with respect to the matrix located right here. So this is what would happen. And one thing that's interesting to note is that in the forward pass, all we do is W times X, because you're just combining elements from different sources and mapping them to, if it's an M by N matrix, then basically the limited M outputs. Here, what you would do is work with the transpose of the matrix, because that basically has the property of redistributing exactly these errors in a backward manner so that it accumulates them to the correct sources. And this might seem familiar if you've done any sort of like network analysis or something. Similar techniques are used there too. So these are the 2 basic patterns that we need to notice. Now I want to just describe the same exact network using a much simpler block diagram, because this will help you do things much quicker in the exam. So this matrix over here, this network over here can be represented as a Z1 coming in, that's right here. It goes through a unit of 1s, doesn't do much, produces an activation A1, goes through a matrix W1 located right here, which is drawn here. That produces a vector Z2, that's the 2-element vector right here. Goes through a sigmoidal unit, produces an activation, goes through a W2 matrix located here, produces Z3, and passes through 1 and creates an activation. So at this point, we're going to use this diagram a lot. So I want to just stop and ask you if this diagram makes sense to everyone, because this diagram is going to be like extremely useful. All this complexity will reduce to something that's so beautiful and elegant. It's just awesome. So does this diagram make sense? Yeah.
In the top diagram, how do we tell what the nonlinearity associated with each neuron is?
This particular one?
Or like say the input neurons or the output neuron, whichever.
So are you asking me how do we tell if...
Sigmoid or softmax.
Oh, so in the exam or something like that, you would be explicitly given what the nonlinearity is. Ideally, I shouldn't have been sloppy and I should have put a sigmoid here, but I clearly didn't. The ones here are the same ones here. So ideally, there should be sigmoids here, and that should be pretty clear. Now, I mean, conventionally you would have the same operation applied here and here, so a single one should be sufficient. But if it weren't, you could split this up and just write it in the same manner. Like say there was like, a softmax here and tanh here. Now I don't know why you would want to do that, but if you had some intuition as to why, you could basically draw that out in the same exact manner. So does that answer the question? All right, any more? So we'll just go with this particular diagram and we'll do forward pass, backward. We'll do backward pass using this now. So the first thing I want to do is that I move the error backwards from this point to this point. Now note that we're doing things in a vectorized manner. If this was a softmax function, this would be y hat minus y. You already know how to calculate this. So this would be y hat minus y. And like I said, every time I am at a z location, I will also, annotate it with a delta location, which will mark the error propagating backwards there. Okay. So this is delta 3 located right here at this left line, and this is the error propagating backwards. Now I want to move, so at this point you can do the gradient with respect to W2, because like we discussed, all you need to do is the outer product of the inputs that W was forwarding, it was responsible for forwarding, and basically the error that's propagating backwards. It's a pretty neat intuition that the gradients of any particular parameter are completely dependent on things it forwarded, things it was responsible for forwarding. So it was its job to do it right, and clearly there was an error, and a boss from upstream is coming and complaining that, well, you need to pull things together. So this is how you would calculate the gradient, the outer product. We discussed exactly how to do this. And now I'm going to use this delta, which is why we keep emphasizing the use of delta. I'm going to reuse this delta 3 to calculate gradients, downstream. So I'll move this delta 3 across this affine transformation using the W2 transpose. Like I already mentioned, the W2 transpose comes into play because you are mapping backwards the error gradient. So if there's an error vector delta coming here, and we used W2A2 to generate Z3, now all we need to do is W2 transpose delta 3 in order to move the error across the matrix at this point. And this is like one of the key patterns that you'll notice in all of backpropagation, and you should be really familiar with this for the midterm so that it'll save you a lot of time. It's also applicable to RNNs, but I won't get into that because Ian's going to discuss that in much more detail later. So, and you'll notice that the dimensions actually line up perfectly too. One thing I want to point out is that when you typically do a gradient, using chain rule, we typically write, something like df dx as df dz, then dz dx. Something like this in this form, but when you're working with matrices, it's much more helpful to just move the things that are coming in downstream to this side. It'll make your matrix math work out, and that's the reason we keep this W2 to the left of delta 3, W2 transpose to the left of delta 3. So a lot of people in office hours came and said that, well, I'm applying the chain rule and the dimensions aren't matching up. Well, you were just not putting it in the right place, because when you're working with matrices, your input vector is to the right, then you put an affine transformation to the left of it, and then get an output. So just keep this in mind, so that you don't stumble across this. So you move this. At this point, you have an error vector, W2 transpose delta 3. Now you want to move across this pointwise nonlinearity, and the trick to do that is basically the error that was propagating backwards is just multiplied in a pointwise fashion with the local gradient at this point. So you have a sigma. So you basically have a sigma prime of Z2, that's the local gradient at this point, and you multiply that in a pointwise manner with the error located in this location. Again, notice that I put this on the left. You could also write this in terms of a diagonal matrix, but you really don't need to. You can work with this as well, and it should just work out just fine. So this is how you move across this pointwise nonlinearity. And now you'll see that we're going to just basically be applying these tricks over and over again to calculate really complex networks. Again, now I'm going to save this as delta 2 just to point out, since we are at a Z2, and by law, we are going to call this delta 2. And then again, we're going to move across this matrix W1 over here. In the same manner, W1 transpose delta 2, redistributing the errors backwards. So that leaves us with the gradient. And at this point, we can actually even calculate the gradient of W1, which is the outer product delta 2 at this point, and the input A1 transposed. And now I want to just go through a much more complex network. So here we have a softmax loss. We have 3 input layers, but everything is going to follow through in the exact same manner, so we can sort of rush through it. Here we basically have a predicted value yp, y sub p. I would have called it y hat, but PowerPoint is not that friendly. And yeah, let's start. So we start with the error propagating backwards, which is yp minus y. I'm going to call this delta 4. We move across the W3 matrix, so you have W3 delta 4. And you get the error moving. That's the error at this point. You can also calculate the gradient at this point in time. Then you move across this pointwise nonlinearity by applying a dot product. Again, everything is multiplied to the left-hand side. And then again, you move across the second affine transformation. And then you basically do exactly the same process again. And you can calculate the gradient again. And lastly, in case you have to do any gradients with respect to the input vector, you actually have just done it. When you have the error at this point, actually when you have the error at this point right here, Z1, which happens to be the error at this point, you've actually got the gradient with respect to the input vector as well. So that's basically all the error that's remaining to still get redistributed. That's the remaining part, of the error that's still, the blame needs to be assigned for. So that's that. Hopefully you feel much more comfortable with backprop now, and all you just need to know is these couple of tricks and know how these fall into place with each other, and you should be able to work with most networks. Yeah.
The exam when we're performing derivations.
Yes.
Can we use the matrix forms as a building block, like an assumed building block, or are we going to be, or is it going to be important to be able to derive?
Correct me if I'm wrong, but as long as you convey the intuition that you're trying to move the error backwards, I think we'd be happier with that than backpropagation. So as long as it's clear what you're trying to do, and it's clear that this is a result of chain rule. We haven't really done anything that's not chain rule here. So as long as it's a result of chain rule, it's perfectly fair game in my opinion. Richard, correct me if I'm wrong though.
Yeah, so we want to make sure you understand what you're doing. We don't want you to just write down, well, I memorized that one equation from the lecture, and so I'll just plug it in right here because it's a neural network. What could possibly go wrong?
Right.
And maybe you get lucky, and maybe it's a different formulation that is slightly, odd. So you need to very clearly show every single step. So if you use this kind of rule, then say, well, for a simple form, this is how you take the derivative of wx, with respect to w or something like that, and hence now I can plug that in. And so in the end, backpropagation is just a terminology for not redoing the same gradients multiple times, but you're still just computing gradients. So.
Yeah. Any more questions regarding this stuff? Yeah.
Yeah, so all of this seems like totally understandable, but I'm still not sure why it's sort of like easier and better to do than just normal chain rule on matrix derivatives and then keeping track of intermediate values.
It's not necessarily better. It's a more followed convention. I would say it makes your math much more readable and interpretable. So that's one reason to do it. The second reason is just that usually we've noticed it's a pedagogical tool where we found that people typically mess up when they're doing chain rule. Things like this happen, and then you'll realize that your dimensions don't line up. And but if you're comfortable with doing that, that's perfectly acceptable too. I don't see any reason why that's not.
Would it be possible to post these slides?
Yes, yeah, these will be posted online so that, we expect you to go through these and convince yourself that these are in fact true. We just went over it really quickly. Yeah. Any more? Cool, I think I'll give it to Ian next to take over the next section.
Can you hear me? Okay, so I want to pick up roughly where Rohit left off, and we'll make sure. Oh, that's why this is not open in proper slides. Can you get it to just switch? Yeah. Slideshow. Okay, here we go. So I want to pick up roughly where Rohit left off, and we're going to do backpropagation on a couple networks, both of which you've seen before, but using this formalism of pushing back error vectors and doing everything in the form of matrix ops. So you've seen how we can go from having slides that should not be auto-advancing on me, from having like individual neurons and all these like fully connected layers in this dense massive connections, and really we can just express that in terms of matrix ops that handle all of this combined with the pointwise nonlinearity. So we're gonna, for the first part of this, we're gonna talk about this simple recurrent neural network, and you guys have seen this. This is basically the network from assignment 2 that we've also discussed in lecture. It's also called an Elman network. And the idea of this is that it's really just the same as this sort of 2-layer, 3-layer, depending on what terminology you use, neural network, except there's input from previous time steps. So this is sort of a single time step. You have X, and then there's the hidden layer, and that takes X and the previous hidden layers as input, and then it makes a prediction Y hat. So these are the equations for it. You've pretty much seen these before. And sometimes to analyze this, it helps to unroll it in time. So really you can think of this as, you know, this is this thing that's dynamic. It can go over sequences of different length because the recurrence defines how it's going to behave there. But you could, like given, let's say you have an input of 3 items, you can just unroll the network as this full like grounded thing that has discrete nodes. And the only difference between this and like any other normal feed-forward network with the same architecture is that you share parameters. And sharing parameters isn't anything special, really. You can just do backprop on this, and it just means that you store the gradients multiple times for the same thing. So in order to backprop on this, we're going to take the usual, for this example, we'll just take the cross entropy loss. So this should be super familiar if you just finished assignment 2. And then at the first time step, we have a lot of gradients to take. This looks bad, but it gets worse because we need to go backprop and do even more things at previous time steps. But as Rohit showed you, there's only a handful of little building blocks that this is made out of. So looks like a lot of math. Actually, it turns out it's not so bad. And the reason for this is that we can express everything in terms of these affine transformations and then activation functions. So if we just look at the output layer, Y hat, we have softmax applied to this thing we'll call A, which is just a matrix plus a bias term of our hidden layer. So we want to take the gradient to it. You guys have seen this expression for delta before for this kind of layer, Y hat minus Y. Hope you guys got that. Just to kind of go off of what you need to switch around the chain rule thing, this is a part where mathematicians and especially machine learning people are not at all consistent about. But a lot of the times, at least the way we usually write the chain rule going from right to left, it means that those elements in the chain rule, and a lot of you guys have come to office hours asking about this, they're the transpose of what we call the gradient. And so if you think of these derivatives of having like J is a scalar and A is some vector, so this thing has dimensions of, so this thing in here has dimensions of 1 times K, where K is the dimension of the vector. Take the transpose, that's our gradient, that's a column vector that we usually deal with. Remember that if you're taking transposes and matrix ops, if you were writing them right to left, now you write them left to right, so you just invert the order of things. If that's confusing at all, then the way to think of it is just, sorry, I didn't show that yet. The order in which you apply these transformations as you're going backwards, it's the reverse order that they appeared in the network. So if you do a matrix and then some nonlinearity, then you're going backwards, you do the nonlinearity and then the matrix. And when you're going backwards through a matrix, you take the transpose. So if we do that here, we're just going through this nonlinearity, and we see that for the simple gradient, just with respect to bias term, is what you guys have seen. It's just delta. And if you write it this way, using the chain rule and just take the transpose later to get the gradient, you see that the dimensions work out. So you get 1 by k by k, because remember that this thing is the identity matrix, really. So you get these diagonal matrices. And this works out. The row vector, take the transpose. It's the column vector we want. This gets a little weird when you're dealing with matrices. And technically this thing, you can put these in parentheses and not worry about it. Technically it's some third order tensor that has a bunch of repeated rows. Usually we're just not going to worry about it, and we know our expression for the gradient with respect to a matrix, and it's this outer product. And gradient has the same shape as the matrix, right? It's the transpose of this thing. And get that to go away. Not what I wanted. Anyway, so if you were to code this up, you could use just this handy thing for outer product. There we go. So if we want to go back further in time, we could do these out explicitly, but we don't really need to, because again, at each layer, we're just going to have the same structure, right? There's going to be some affine transformation, and then there's going to be pointwise nonlinearity. And I wrote it f, in the expressions below I use sigmoid derivative, but really this can be whatever you want. So if it's tan h, instead of f times 1 minus f, you use something, 1 minus f squared. Other functions, it's so unlike ReLUs, it's this piecewise thing. And the idea is that we want to be able to write deltas. So you've probably seen this expression. You go back, right? So delta, your delta that gets sent to the affine part of the output layer, we're going to run it backwards through the matrix, and then we're going to run it backwards through the nonlinearity. And really, right, this is just a chain rule expansion where we go here to the affine layer, and then through that matrix, and then through the question? What? Yeah.
Why is there 2 superscripts on the delta?
So I try to keep with the notation of Rohit's slides in that 2 is a second layer. So if you go back to this, the idea is that there's sort of 2 layers separating your input and your output. And so your delta 2 kind of lives here. And delta 1 is for the first layer, which is the hidden layer. It's a little tricky. There isn't really a standardized notation for doing this over time. So really, these are just taking the chain rule. And if you were to write out the chain rule for the actual parameters that you're interested in, you can see that you write out the chain rule and you get these expressions that have some common prefix. And so, right, you go, to this first affine, and through the matrix, then through the nonlinearity, and then now you want to take the derivative with respect to B1. So you can just put parentheses around this first part, and that ends up being the delta term for that layer. So it's the same idea, right? It's just, if you were to do your chain rule all the way from the beginning, you just kind of save your work because everything past that point is going to reuse the previous segment of the path. So if you do it this way, then you get kind of a common form for all the gradients at each layer. So you have the delta input to the layer, times here's the derivative with respect to the bias, here's the derivative with respect to the matrix. Again, you want to kind of use the outer product shortcut here, but you use the same delta that feeds into that. And then if we want to go back in time, we need to go sort of step 1 back to the hidden layer, or to the previous layer, so we can look at the input to that hidden layer, take the derivative here, and again, it's got the same prefix, so we feed in delta. Yes?
Shouldn't it be a Z, the last sentence?
Oh, DZT, that should be an H there. Oh, yeah, you're right, this should be a Z. I think the expression here is correct, though, which is what you want, because again, you're going to feed it through, right? There's a matrix at this layer, you send it backwards through the matrix, and then backwards through the nonlinearity, and then you get to the previous affine layer. Any other questions? Yeah. Yeah, so I wrote it as the transpose so that we can write the chain rules from right to left, and so the transpose is a row vector, but usually in your code and in math we deal with them as column vectors. So this should be correct because that's a row vector on the left there, and this should also be correct because this is a column vector on the right. So the rule of thumb there is that you have to be a little bit careful of square matrices, but just remember that when you're going backwards, you take the transpose, and if you're not dealing with square matrices, there's really like only one order you can do things that make the dimensions work out. And so again, there's sort of the usual shortcuts, right? If you have the bias term that's just added, the derivative is just delta because there's that identity matrix we saw before. We just pretend that it's not even there. With respect to the matrix, you take this outer product and you look at this. This has the right shape. This has the same. This expression ends up with the same shape as H, because this delta is the shape has the number of elements equal to the input, the output of H, and this has the input to H. And then if we go back one layer, it's like we saw before. You go back through the matrix, back through the nonlinearity, and that just gets you to the previous time step, and you can just repeat that recursively, recurrently. And keep performing backpropagation through time all the way to the beginning of the sequence. So any questions about that before we move on to slightly more complicated graphs? Okay. So that was a lot. But it gets sort of worse. And so you guys remember the lecture where we talked about more complicated types of recurrent networks, and so you have different types of units. So in the simple network we just described, that you guys did on assignment 2, it's just an affine and then a pointwise nonlinearity at each hidden unit, and it takes the hidden and the data as inputs. But you can make these units more complicated. So sort of the simpler of the two examples, we're not going to worry about LSTMs, but is a GRU. So these are gated recurrent units, and the idea is that if one of these replaces this simple affine hidden unit that you had before. So the input here is your data xt and the previous hidden layer, and the output is the value of that hidden layer before. So you can kind of think of this as fitting into your network architecture as a black box, but inside it's got some internal structure that's interesting. And the idea is that it has these reset gates and an output gate, and it lets it decide whether it wants to take into account new inputs, throw out the old memory. Yeah?
BackProp on GRUs is part of the Midterm course.
Can neither confirm nor deny, but it might be good to know. It can neither confirm nor deny that it may be on the midterm. But it would be good. I mean, in general, understanding how these things work is good practice for any kind of problems that we could put on there.
Because what Richard said is different from what you said.
Does Richard want to chime in?
That lecture, you need to be able to derive. You still need to understand how it works.
It's an hour and 15 midterm, so there won't be, every single thing we covered in lecture won't fit on there. But it will be helpful. So we're going to go through this as an example, just so you can see how we can do backpropagation on kind of an arbitrary graph. Before, we've seen that there's basically one way that information can flow. So if we go back to this, right, if you're looking at the loss function here, there's only one path from this loss function down to x, to x t minus 1, and so on. You follow a single path that's through the graph. But if you make things more complicated, so if you look at the GRU, the idea of this is that everything in this hidden layer, and there's a bunch of these different little elements, they all depend on the previous hidden layer and the input x. So again, we have this what's called the output gate C, reset gate R. These things, they have a sigmoid activation function, so they end up between 0 and 1, and that lets, basically, you can think of it as a switch. If it's 1, it's on. If it's 0, it's off, and it's got a continuous function, so you can take gradients. And then there's this H tilde thing that is sort of a candidate hidden layer, and basically that gets prepared as if it were just a normal recurrent network, and then sort of based on the input from the reset gate, and then gets mixed into the output based on the value of the output gate. So the idea is that if the reset gate is 0, it completely ignores the previous hidden state, only computes h tilde based on the new state, so on. So we're not going to worry too much about that for now, although it would be a good exercise to go look through the equations and try to understand sort of intuitively what's happening, maybe sketch out like some simple numbers and see if you can get the network to mimic some behavior that you think is interesting. Yeah?
Just another question. So some of the networks like the RNNs, some people like to insert biases and didn't insert them.
Yeah, I just left them out because there's enough math on the slides anyway. You can insert them.
During the midterm, are we supposed to memorize a version of those networks?
I wouldn't.
We will define every forward, like the backpropagation is always falls very deterministically from the forward propagation. We'll always tell you the forward propagation. You never have to just memorize like this was a GRU or this was, you know, like a recurrent neural network. We'll tell you exactly what the forward propagation is.
Yeah, I mean, you should be able, like, if you see a network that looks like something you've seen before and there's a bias term and there wasn't before, it shouldn't really change anything else. Yeah.
You don't need to memorize. Actually, one really nice trick about the bias term, should have mentioned before. You can actually imagine you have your W here, and now you have your X term here. Turns out if you just added 1 to the end of your X, now you can think of like where to put the bias term inside this W as like another row or column, and then you actually get exactly the same. And then you don't even need to think of the bias term again.
Yep.
Write this down and think about it. It's actually a neat idea to only have one equation.
Yep. Yeah. So in that case, in that sense, therefore, you know, the bias gradients with respect to the bias term end up being just like a subset of the elements of the matrix. So here are the full equations for the model. This looks like a lot, but again, remember, look for patterns, right? You see each of these as some affine. Again, we're just omitting the bias for now, with sigmoid activation function. So ZT and RT have this, you know, they take the same inputs. They have their own matrices, but they've got the same form otherwise. H tilde, you know, takes, it's an affine of the input and an affine of the previous hidden layer with this element-wise multiplication applied. And this is the, you know, the reset gate. If it's 0 at some element, that basically means like ignore the value of the previous hidden layer for that neuron. And then there's a tanh on there. And then we do this mixing, which is, you know, ZT. This for the output gate's high, it just carries over the last hidden state, and if it's low, it's going to mix it with the new state, the candidate state. So look at these equations. Now we're going to try to go backprop on these with respect to the input x of t. And you'll see how this gets a little bit tricky. So we want to compute this. And let's say we've already computed the error delta. So the error delta is going to be the delta. It's the error vector right at the input here going into the hidden layer. It's the same as the deltas in our simple neural network. We're just going to pass them through a more complicated blob. And then, so that feeds into sort of the last node in the output, which is h of t. And this is defined this way. And so we have to expand out the chain rule into a sum because we've got a sum of terms, and two of those terms are products. So we end up with 4 different terms. The product rule here, right, it's element-wise multiplication, so the product rule looks just like the product rule for scalars. So you need to, you know, check each side of the product, and you need to account for the sum. So we can write this out. Remember that each of these are multiplied on the left by this error delta, which is, you know, in this formalism row vector. And so we can work on this a little bit. We notice that this first term doesn't depend on x, so we can just drop it because, you know, the previous hidden layer doesn't depend on the input at the current time because it's only going forward. And we can just combine things, right? d1 dx is also 0, so you could drop that. And so now we end up with these 3 derivatives we need to take, right? There's element-wise multiplications with things we've already computed, and presumably those are stored somewhere, so you can do this efficiently. So we need to take dz dx, dh tilde dx, and, well, dz dx again, so we can just reuse that. And remember that this is just our delta. So For the output gate, this is just the standard gradient with respect to a affine layer with a sigmoid activation function. Again, the gradient is the transpose of this. We're just going to write out derivatives so we can use the chain rule. So the matrix is not transposed in this. You go through the nonlinearity and then you go through the matrix. And the element-wise multiplication, you may have seen this technically, it's a diagonal matrix, but maybe it's more convenient to write it this way. It's completely equivalent. So that's the output gate. Now for h tilde, we have to take into account that there are two terms. So naively, we have the same thing. This is the gradient for tan h, and we element-wise multiply it with the matrix w that gets applied to x. But the problem is it also depends on r. And so we've got to go one more step back in the chain rule and account for dr dt, or sorry, dr dx. So again, you go through the nonlinearity and then you take this gradient and then you do element-wise multiplication with the thing that was on the right of that. Yeah?
So in the first term of the sum for the derivative of h tilde, when you use the Hadamard product, is that assuming that it broadcasts like you were coding it, or this technically that's not a one-point?
Yes. Yeah. We use I'm using the Hadamard product basically as like shorthand for writing like this thing is a diagonal matrix with those things on the diagonal, and in that case it does multiply properly if you check the dimensions, right? Because this is if z is 10 dimensions, this is really a 10 by 10 matrix, diagonal matrix, and this is also happens to be this is 10 by like maybe the input's 15, so the 10 by 15 multiplies on the left 10 by 10. That's okay. Any other questions on this? Yeah, in the back.
You're saying you would multiply it by the arrow, not by the matrix?
So.
I would say it's like multiplied with a vector of 1.
If you do the Hadamard product, remember that this is only part of your expression. It's really this whole thing that this whole like z at t times 1 minus z at t. Formally, if you want to write out the chain rule and have the dimensions match, this should be a diagonal matrix. And remember that you're also multiplying on the left by something. So you could think, right, matrix multiplication is not commutative, but is associative. So you could just multiply, like you could do the element-wise multiplication with the thing on the left, and then you just get a vector, and then you can multiply it by w without any trouble. I'm just not writing out like diag of this because it's going to make these equations even longer. So yeah, turns out we need to compute this third thing. Fortunately, we've already done it for the output layer, and the reset gate the output gate. The reset gate has pretty much the same form, so we can reuse this expression. So again, here's the derivative of the nonlinearity, and then here's the matrix to go through those in that order. And so now, at this point, you can just add things up. We've got all the expressions, they're written down somewhere. We know everything is expressed in terms of something we've already computed. Either it's one of the parameters or it's the output of one of these gates. We're not going to do that now because it's a pain. There's a lot of terms. But if you think about if you were to code this up, right, you could call this like dr dx or something, and that's a vector, or sorry, that's a matrix. And you can multiply it on the left by your delta, and that gives you the gradient you need. So just kind of to tie it all together, why did we need to take these three derivatives? So this is you get the network we showed before was the view of the groove from the paper, and it's sometimes simpler to think about its sort of forward operation that way. But if you want to really visualize all the connections, this is the figure we had in lecture. And if you look at the X node, there are these three paths coming out of it. There's three different things that depend on it, or there's three arrows coming out of it. So there's three different things that depend on it. So we would have to compute these derivatives in three different places because we have to account for all the possible paths from where the error comes in, which is right here, flowing back to the node that we're interested in, which is down here. And it turns out that if you remember back from a few slides ago, that we have the dz dx appears twice. If you look at this graph, you can see that there's this path split. So if you go from X to Z, there's two places that gradient comes in and influences, or that information comes in and influences the output. So when you're going back, you have to follow both paths and sum them up. Again, this is really, it's really just the chain rule applied to products, right? You have to expand things out into a sum, account for every possible path of information flow. So yeah, you sum this up, you get 4 paths total. There are 4 terms in the original equation, and so on. So GRUs are complicated, but this is well within your ability to solve, because you can just write out the equations and you see that all the pieces are pretty simple. They're all things we've seen before on simpler networks. And if you compartmentalize, you put parentheses around things, pre-compute them, call them a delta, then it's just a matter of passing an error vector, through simple elements that you've seen before, right? It's just, we just have a handful of simple operations that we're composing to get these complex networks. So, any questions on GRUs? Okay, so just to wrap up, the moral of the story is check your dimensions, write out the chain rule, put parentheses around it, but if you're not sure if something works, make sure you're doing legal matrix multiplications, because that will check a lot of errors. Feed things through. When you're going forward, you feed things through operations in one order. When you're going backwards, send them through in the reverse order. And then by doing that, you can combine simple operations, really just a handful of them, to make a pretty complex network. All right, good luck, everybody. And Peng? Go.
Make sure you slow down. I know it's super awkward when people are like, do you have any questions? It feels like an eternity. Just give it like 5, count to like 5 or 10 when you ask if there are any questions.
So I guess for the last 20 or so minutes, I'm gonna walk you guys through the word vectors, which are kind of an important building block of a lot of deep NLP algorithms. So basically, we'll revisit word2vec and glove briefly, and I'll walk you through an example where I can show you that you can actually derive the gradients for word2vec with backprop, which is a lot easier, I think. So first with word2vec, remember that we talked in class about one of the word2vec models, which is skipgram, where the task is given a center word, we want to predict all the context words, right? And for this task, for each word, we associate 2 vectors with it. One input word vector and one output vector. And in assignment 1, we've seen 2 kinds of costs given these vectors. One is the cross entropy cost, where you just form a huge softmax from the input and output word vectors and do a cross entropy on that. The other is negative sampling, where you do something a lot simpler. As you've seen in problem set 1, this requires a lot less multiplication, and it can be a lot more efficiently computed. So conceptually, these 2 kinds of costs are doing the same thing. They're trying to, given a vector prediction and the vector that you're expecting, they're trying to maximize the inner product between those vectors, meanwhile minimizing the inner products between your predicted vector and all the other vectors. And note that in skipgram, this R thing, or this vector prediction thing, is just the input vector of the center word. But why do we bother to introduce all these notations? That'll be a bit more clearer when we review a continuous backwards model. So to put things together, for skipgram, when we have a full context window, we just sum all the costs for each pair of words, each pair of your center word and one of the context words. we're introducing all these notations actually to simplify your computation, because as you can see from your problem set 1 and from what Rohit and Ian have presented, if you're splitting these things into simpler blocks, you know how to do each block, then things will be simpler if you view it that way, if you propagate the errors back. So why the notations? So it turns out when you're comparing the continuous backwards model with our skipgram, the task is kind of opposite. For skipgram, we're trying to predict the context from the center word, but for CBAL, we're trying to predict the center word from the context. So here, whereas we have the input vector for the center word as the vector prediction, for CBAL, we have a function of all the input vectors in the context. And in our assignment, we just summed all of these vectors up to simplify your gradient computation. Also, during office hours and on Piazza, some students were asking about how to intuitively understand word-to-vec. And here is my attempt to answer that question. Hopefully, it'll be clearer after this. So remember, when we're trying to factorize a matrix, say we want to factorize an n by n matrix to low-rank factors, each element in the original matrix can be rewritten as the inner product of a row in the left matrix and a column in the right matrix. That makes sense? So moving on, imagine you're given a matrix to factor, but you can only observe this matrix is a matrix of counts, but you can only observe the pairs one by one. So how should we go about factorizing this matrix? Given this observation, whenever we see a pair that we want to, whenever we see a pair in the matrix, we observe this pair. We want to increase this inner product term, right? Because we said each element in the factorization is actually the inner product between these two. And is that enough? Actually, it turns out no, because there are a lot of pairs that we won't ever observe. So while we're doing this, we might also want to push all the other vectors or minimize the inner product between these vectors and all the other unrelated vectors. So in a similar sense, we're trying to pull these two together while pushing away all the other vectors. Did that ring a bell? Because we were just saying in skipgram or in word2vec, the cost functions are trying to pull the vectors you predicted and the actual word vectors together while pushing all the other vectors away. So if you remember from the lecture that we saw from the word co-occurrence matrix that if a word co-occurs with some other words in the context, they might share a similar meaning, right? And that's roughly what we're doing in word2vec. And there was a question about, but why would you use an input vector and an output vector for a word? And I guess my interpretation is that if you're using two sets of vectors, it's usually less constrained on the optimization problem, and it's easier to optimize that way. Any questions so far? Cool. Let's move on to a simple comparison between the glove word vectors and word2vec. So remember from the lecture that the glove word vectors are kind of operating on the word co-occurrence matrix, modulo the fact that they're doing some smart logarithm transformations. So that fact makes the training fast, because for word-to-vec, if we want to train a word-to-vec model on a large corpus, we really need to go through each of the windows, each of the context windows, right? So effectively, for the number, your algorithm runs in linear time of the number of context windows you have. But Glove is free from that. And by directly using the word concurrence matrix, it has a better, more efficient usage of the co-occurrence statistics. If you're unsure about anything that I just mentioned, please try to go back and review, I believe it's lecture 2. Lastly, I'm gonna just present you a simpler derivation for the word-to-vec models and the gradients we've looked at. So in class, we derived the gradients for this softmax cost function. We expanded out, basically, expanded the log to log A over B to log A minus log B, and blah, blah, blah. We derived everything in one step. But here I'm going to show you that first we can complicate the problem by splitting it into multiple operations, and then doing a backprop, which is super fast. So you can verify that we can rewrite this complicated formula into these 3 steps. First, we compute the inner product between your input word vector with all of the output word vectors. You obtain a theta vector this way, and you can apply the softmax, then the cross entropy loss. We've done this multiple times. Does anyone remember what's the partial derivative with regard to the thetas? If you have such a formation like cross entropy and softmax? Softmax minus or 1 hot, right? And now everything's a lot more clear, because you know the gradients from your cost function to the thetas, and the theta is actually a matrix vector multiplication. Rohit and Ian were walking through this over and over again, right? If you want to derive the gradients to the matrix, you just do an outer product. If you want to derive the gradients to the input word vector, you just like transpose your matrix and multiply that by your error information. And that's your gradients right there. You can try to verify it with against your answers in problem set 2. And you'll see this is actually a lot easier to compute, and this is actually a lot more vectorized to implement. Any questions? Okay. Turns out I used the same mean. Good luck, everyone. Richard, do you want to wrap up?
So, yes, that was the material. I may have been a little fast, maybe. But are there any other questions about what you've seen today? Yes?
I guess related, I mean, this has come up a few times, but how strict would you guys be with, like, because there's been, a few conventions of people have different ways of, like, doing the chain rule left to right to left, transposing here and there. But, like, you guys will be okay with, as long as the final answer is
As well, as long as the final answer is right and every single step made sense
within the convention.
Within the conventions that you choose, then you're good. But, if you switch a bunch of conventions, one line is actually wrong, and in the end you get the right answer, you're not going to get full credit, because it's clear you kind of just try to memorize some equation and you can't really follow the steps through. And if in doubt, always stick to the stuff in the class. In fact, I kind of want to apologize for having sometimes slightly different notation. I should have forced everybody to more clearly look at and use exactly the same in the class. So if you're confused, just always use the one in the class. If you are familiar with other ones, they're actually fun story. I worked once with a physics PhD at Stanford, and I asked him, first thing to do, derive all the equations. And he basically wrote a bunch of stuff, and it looked totally random to me. I'm like, what's going on? He's like, it's Einstein notation. I'm like, Einstein notation, right? And so looked it up, and that's what physics, people use. They just have all their indices because they have like 4-dimensional tensors, and so they need to write it just completely differently. And so, don't introduce Einstein notation ideally in the midterm to the TAs, but if you clearly write out and define your notation and your formulations, you'll be on the safe side.